Hello, chemists. I hope that you have accessed your notes for Charles Law and have read in your textbook and watched that short little video on Charles Law. So I hope you have your calculator handy as well. With Charles' law, as temperature increases, the volume of a gas is also going to increase if we keep the pressure constant and the amount of gas that we have present constant. So, as the temperature goes up, gas particles move faster. They collide with the walls of their container more frequently and with greater force. So, the pressure has to be the same, unchanged, for the volume to actually increase. Whenever we're working with Charles' law, we absolutely have to use the Kelvin scale. If you just keep the temperature in Celsius, your problems are going to work out wrong. Trust me on this. We've tried it many times. So to go from Celsius to Kelvin, you have to add 273. So remember, if you're given Celsius, add 273 to get it into Kelvin. So with Charles' law, whenever you double the temperature, the volume is actually going to double, but only if you are using Kelvin. So every time you increase the temperature by 1 degree Kelvin, the volume is going to increase by 1 273rds. So here we have two little scenarios. We have a piston pushing down on our gas particles that are in this cylinder, and it's just atmospheric pressure, 1 atmosphere of pressure. And look at the volume, 300 milliliters, and the temperature is 150 Kelvin. So in that same cylinder, if we heat up the gas to 300 Kelvin, the volume is going to double. It increases from 300 to 600. And we still have the same amount of atmospheric pressure, standard atmospheric pressure, 1 atm, pushing down on that piston. So if we take a look here in this graph, as the temperature increases, so does the volume. Now there's only one standard temperature, and that's 273 Kelvin. There's many standard pressures, as you recall in Boyle's law. Absolute zero would be 0 Kelvin. We can get pretty close to absolute zero, but we can't quite achieve it. All particle motion should stop at absolute zero. So the molecules stop vibrating in place, the electrons stop spinning on their axes, the electrons stop orbiting around the nucleus. All particle motion should stop. We can get very close. We've almost achieved it, but not quite. Anyway, with Charles' law, here's our formula. Volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. And just like with Boyle's law, if you know any of the three variables, you can solve for the fourth variable. So here's our first example. We've got 225 milliliters of gas collected at 58 degrees Celsius. What volume will the sample occupy at standard temperature? So the first thing we do is list our given. So we want to write down all of our known information. 225 mils of gas. What do you think that is? I hope you said V1. Collected at 58 Celsius. So that's our temperature one. Now we can't keep it in Celsius. We have to get it into Kelvin. So what do we need to do? Add 273. And that comes out to be 331 A for Kelvin. What volume will this sample occupy? So that's what we're solving for. We don't know what it is, we'll put a question mark next to it. T2 is standard temperature. So what is standard temperature? We just went over it in our notes. 273 Kelvin. So our formula for Charles' law is volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. Now, in this case, we need to solve for volume 2. Volume 2 is already in the numerator position. So what we need to do is undo the division of temperature 2. So we're going to put T2 on top on both sides. T2 will cancel here. And look, we've got V2 by itself, our unknown variable, on one side, with all of our known variables on the other side. Okay, so here is our rearranged formula, and this here is what you're going to need to have written on your homework paper. Don't forget, you always want to list your given, write the formula that you're working with, solving for the one unknown variable and having the known variables on the other side. And now we need to just substitute in. And it doesn't matter if you have the V1 listed first and then the T2, or the T2 listed first, then the V1, as long as both of those are on the top in the numerator position, and the T1 is in the denominator position. So T2 is 273 Kelvin. And we're going to multiply that by V1, which is 225 milliliters. And we are dividing by T1, which is 331 Kelvin. Kelvin units cancel. Take your calculator, take 273 times 225. Divide by 331. And we get, for volume 2, 186 milliliters. If we want to maintain the 3 significant digits that we had originally in our volume 2 or volume 1. So if you examine this, take a look. Our temperature dropped. We went from 331 down to 273. So we would expect that the volume would drop. And it did. It went from 225 milliliters down to 186 milliliters. So that makes sense. That's just kind of a quick little mental check. So let's work on example number 2. A gas occupies a volume of 750 milliliters at a temperature of 122 Celsius. To what temperature in Celsius must the gas be lowered if it is to occupy 500 milliliters? Now, we still have to do all of the work in Kelvin using the Kelvin scale, and then we would convert back into Celsius. So just like before, we need to list our given. So volume 1 is 750 milliliters. Always make sure you include your units there. Temperature 1 is 122 Celsius. And we need to add 273 to get it into Kelvin. That brings us to 395 Kelvin. We need to solve for temperature 2 and put it back into Celsius. And volume 2 is 500 milliliters. Now, you might look at that and say, well, temperature's already in Celsius and I need to have my answer in Celsius. Can't I just use Celsius? Trust me, it won't work. You have to use Kelvin. You can try it and you'll see that you will get a totally different answer. If you just keep it in Celsius, it's not going to work. Okay, so our formula. Volume 1 over temperature 1 equals volume 2 over temperature 2. Now, I want you to pay close attention to what we're about to do next. Take a look at where temperature 2 is. It is in the denominator. So what I'm going to need to do is move it into the numerator position. So I'm going to put T2 up here, and what I do to one side, I have to do to the other. Now, T2 is going to cancel off over here. But look, I still have to get T2 all alone by itself and get these two other variables over here on the other side. So V1, if I am multiplying by V1 here, I need to divide by V1. What I do to one side, I have to do to the other. Volume 1 will cancel here. T1 is in the denominator. I have to move it to the top. What I do to one side, I do to the other. And T1 will cancel. So now I have T2, the one variable, the unknown variable that I need to solve for all by itself. And look at what my rearranged formula looks like. T2 equals V2 times T1 divided by V1. So this is the formula that I am going to be using now. So all I have to do is substitute in. V2 is 500 milliliters. times T1, which is 395 Kelvin, divided by volume 1, which is 750 milliliters. It is so important that you include your units in your work. Okay, the milliliters cancel. We're left with Kelvin, 500 times 395 divided by 750. Comes out to be 263 Kelvin. Now, pay close attention because it tells us that we need our temperature to be in Celsius. So, what do I need to do to get it back into Celsius? Well, if I'm in Kelvin and I need to go to Celsius, I need to subtract 273. So that gives me negative 10 degrees Celsius. And that is the answer that I am after. Negative 10 degrees Celsius. Okay, so don't forget to submit your notes and complete your worksheet and submit your worksheet. Good luck, you guys. Don't forget, I have office hours anytime you want to check in and get some help.